Okay, so welcome to today's lecture on deep learning and neural networks. And last time we looked in detail into how we can train neural networks efficiently. We looked into some problems like trying to fast converge into a good solution. Anyway, at least get into a very good solution, and a bit about like on overfitting, or at least we explained the problem of overfitting. As the lecture name already says, I mean, nowadays, if we're talking about neural networks, this is often subsumed out under the term of deep learning. And thereby the idea of deep learning is that we're not having shallow networks with 1, 2, or 3 layers, but we really have like large networks where we stack tens or hundreds of layers on top of each other. And therefore, what we today want to focus a bit on is like, okay, if we are now getting these really large networks, is there some additional techniques in order to try to improve things, to make things still working and address challenges that arise then, or at least get stronger? And we'll do that in both things. On the one hand, on the training, how to better deal with these types of networks. And on the other thing, also, again, a bit like some different types of architectures or more additions to the architecture, that the models are better able to deal with these like large networks. So to a bit summarize where we are, this is like the typical way of how you will hopefully currently develop a neural network. If you have some type of problem, you first do your data collection. You try to get some data, supervised data, where you can then train the model to do this type of predictions, class prediction, regression, or any problem you're interested in. Then you should think about the architectural design. So you think about what is like a good like network topology that we can do there. We have learned different like modules that you can easily plug and play. We have the CNNs, TDNNs, we had RNNs and self-attention and state space models. And so you might think based on your model, based on your task, what is like some of the best thing to do. And then we looked last time into like how to do then the training. So then you have the architecture, you put the data into the architecture and let the model train. How this works, we mainly have seen there's like on the one hand this backpropagation, so that we need to accumulate all the derivations in order to know in which direction to update your parameters. And this is a nice thing. This type of training works for all architectures we have seen so far. That's why we consider that, of course, always in our design choice, because we know that this only works if we have the opportunity to calculate a meaningful derivation, which shows us in which way to optimize. Because we saw that when we're training we're trying to minimize the loss, and instead of like just randomly guessing and seeing, oh, this is a good solution and this is a bad solution, it is better to calculate the derivation based on the forward path, calculating the loss, and then calculating the derivation in the backward path and accumulating them over all examples, because then we know in which direction there is a good direction in order to improve, and thereby we can efficiently find somehow solutions for this huge number of parameters. How that works, we had this pseudocode in here. So the main idea is we have to somehow, the question is what examples to consider. So when to update, like doing it after each example was like too noisy. Going over all examples was too slow. So we said typically we're doing these mini batches, that we're going over some examples, accumulating our gradients, and then do an update. Then we have to compute the gradients, sum them up, we saw that we not only need to have the gradients, but maybe also some more things like momentums. Then we have some update rules. We learned different like update rules. I said, I mean, we finished last time with the atom-based algorithm, which is somehow, yeah, currently what is most commonly used. The good thing is it gives you a very good estimation. This, of course, comes a bit with a disadvantage. We have to store quite a lot of other hyperparameters or like additional parameters like the momentum 1 and 2. And we've seen, you remember that this is like a decent amount of additional parameters. If you remember the lecture on GPU, we had there a bit of like how to and where to store your optimizing parameters. So this is, yeah, somehow the basic idea we're having, and this is how all neural networks are trained, which are currently used. However, as often, there is like a lot of details which are important, and why this idea in general is very good and working very well. You often need like have the right things and right like hyperparameters or right configurations in order that this learning really works. Because of course, there's always the danger. We have seen that we don't have a convex function, that you're ending up in a like in a local minima. It might be if you said your learning rate's wrong or has a parameter calculated wrong, that you're ending up training very slow. If you don't be careful, we saw that there's like overfitting. So we have often a lot of parameters so that we are only learning then the examples that we have seen in training, because that is what we're optimizing, but it's not what we're really interested in. We're interested in how good the model performs on unseen data, and then it might be that you're not really working well on that. And when we look at neural models, we see that one thing which makes deep learning so successful is that you quite easily can improve the performance. And the easiest way to improve the performance is to just make the model bigger. To make either more layers, make each layers big, make more parameters, so have a larger hidden size. So there's different ways on doing that. But in general, the idea of just making the model bigger is quite easy. So there's not a lot of like human effort you have to put in. I mean, you just say the parameter, now my hidden size is not 1024, but it's like 5,000. It's like easy to do. And typically, or we will see that if you're doing it right, your model gets better. Or like in the number of layers, we are not doing 1 feed-forward layer, but you're doing 10. And the nice thing is, again, it's machine learning. We just have more parameters. You don't have a lot more work. Of course, the GPU has a lot more work to train, and your inference might be worse, but it's a very convenient way to improve your performance. And we're seeing that this is really like also how it's partly done. So here you see, you might not know, like BERT was one of the first like pre-trained models for text processing. Wasn't like an autoregressive language model, but more like encoding. But it was very successful because it was also pre-trained, has some general knowledge. But if you see how many parameters that has, if we're going in the scale we are currently talking about, this was really minimal. And then you see there's more. Roberta was a version of BERT. You see the BERT in there. And then people looked into GPT-2, which already had some more models. There's like T5, for example. And if you then look at GPT-3, we just like increase the number of parameters by several factors. And this, of course, is on the one hand an easy way, but it's not as easy as it might like first be assumed, because not everything directly works perfectly out of the box. You have to also consider the number of parameters you have, and you might have to adjust a bit. And we want to look especially like what might be important in these cases. And what is in nowadays in most architectures in there. I mean, a lot of these things are even already in BERT, but in general, if you talk about large models, this is really important. Of course, the first thing to do is train on more data. That is the easy, like that is the other thing, how you can improve. The thing is, it's not easy to get more data, especially currently we're looking at supervised data. So how to use other types of data, we'll look then in the next lectures by having a bit of related types of learning things, like not supervised learning, but also looking into transfer learning, by looking into self-supervised learning. That will be like the content of the next lectures. But the other question is, of course, how can you most efficiently learn, like use the data that you have? And that might even get even more important. If you think about GPT-3, GPT-4, nowadays people are talking about that, we're running out of data in the internet. So at least for text, most data that was processed or is in the internet is somehow processed. And although there's huge amounts of text coming in every day, if you compare it to the amount of data that has been there, of course, it's not really huge. So the question is then, how can you more efficiently also learn from the data that you have? So the question is, what does these type of larger models have an effect on your training? I said already, so the main or the easiest ways on how to increase your parameter size is the one way is like making the network wider. So increasing the hidden size here, which would be represented here in more wider networks. And the other thing is making them deeper by stacking more layers. And there again, the easiest thing is we don't have to invent any new type of architecture, like, I don't know, something new compared to self-attention or CNN. But what also is helpful is that you just stack more of them. So you don't take one self-attention layer, but you take 8 or 20 of them. And with this, you can also make things, you can make the model more powerful. But of course, then you also have n times as many parameters. So you have to think about it. So the question is, what does this have an effect on your training? And we're looking into two things which are really problematic with large models. The one thing is, the larger the model is, the more easy the more early you normally get overfitting. That's why in a baseline model, you're not just getting better the bigger, the larger the model is, because if you have a limited amount of training data, it might be better to take a small model because there it can learn. And if you increase your model, it only means you're doing overfitting more early. You more early like overfit to the model, so your performance on your test data might be even worse, even if you do like early stopping and so on. So we'll look into how can we prevent that? How can we also train larger models and maybe a bit restrict again the freedom so that we are not seeing this type of huge amounts of overfitting there, but we are able to perform good training without that. Another problem is that we are also might get more and more into an unstable behavior. So if we're thinking about it, what we're doing is we are calculating the derivation of one parameter with respect to the loss. And then we're going in this direction. So if we're going in this direction, we should then lower the loss. But the implicit assumption is that, of course, all the other parameters are not changed at all. But if we would do that and always only change one parameter, that would, of course, be very inefficient because, if we have millions of parameters, you cannot like iterate millions of times. So in practice, we are updating all parameters all together, and that then might also lead to like correlations we haven't thought of, and the model might get unstable. So we have to think how we can like stabilize the training, how we can calculate efficient the gradients. And in order to do that, we'll look into some techniques today. So especially about overfitting, we'll look into regularization first, and then especially dropout, which is something commonly used in these types of networks. We're also looking at this more from the loss function, so how to like maybe have a more meaningful loss, and that's then referred to as label smoothing. And finally, we'll, at the end of today's lecture, we'll look into a mixture of experts, where the idea is that we do networks that are sparse. So in contrast to what we are doing at the moment, is that everything for each data point, all the calculations is done. So in mixture of expert, the idea is that you have dedicated experts which are calculated only for part of the network. The other problem is then again what we have seen a bit with RNNs, and we're coming to that. Even in normal networks, you then have exploding or vanishing gradients, and we'll look mainly at three things there. On the one hand, different types of normalization techniques. The idea is again that we're staying in a range of values that are somehow good and where the optimization is easy. The other thing is the residual connections, which allow us to faster train and be more efficient. And the other question is, of course, how we initialize our model. So this is the general type of overview we want to look into today. And now we'll go into like each of these points individually. The first idea, in order to prevent overfitting, is it's maybe good to have a large number of parameters, but on the other hand, we only want to make the model use these parameters if they are really helpful. So the model is like somehow automatically using the minimal amount of parameters it needs. So you somehow prefer models where most of the parameters are zero, so don't have really an influence, and only like a small amount of them. And only if this parameter is really, really helpful, then it should be used, and you want to have it a high value. That means if most of our parameters are zero, we're somehow blanking them out or masking them, and only the ones which are necessary are used. So the question is, how can we do that? How can we automatically learn that it will really focus only on the parameters that are important and ignore somehow the other ones? And how that can be done, one way is how we can do a lot of things in neural network. We're having a loss function which tells us try to get as best as possible on the training data. But we already said this is only an approximation. We are not really interested in the loss on the training data. So you can add, and if you have more things you want to tell the network, you can add that in your loss term. So you're no longer optimizing only your original loss, but you're adding additional types of loss to that, telling the model, oh, you should not be only good at performing something, but you should be also good at doing some other stuff. And this can be done here. You see that, so we are adapting our loss by the purple value here, where we are saying, in addition to minimizing our loss on our training data, we also want to have a model which has some regularization function and minimizing that. There's one challenge with these additional losses. Anybody see it here already? It's a bit hidden here. Yes?
Maybe that we have a new hyperparameter?
Yes, exactly. So it's hidden here. We have lambda. So it's lambda times the other loss. So you have to have a like somehow good educated guess on what to put there. And of course, it might depend a bit on your type of task you're doing, because the scale of your loss function might be very different if you use the different types of loss function. So this is, of course, a bit which makes things then difficult, and you have to consider. But in general, of course, it's a nice idea if you want to learn, like make the model learn additional things. You can just calculate what is good and bad for these things and add them as an additional loss in there. So how could this additional regularization term look like? There's typically three things of what to do. So the first thing is like what is referred to as L1 regularization, which just means the absolute value of all your parameter values should be as low as possible, or like, yeah. So you prefer to have all of them as 0. So what are you doing? So you're now having a bit like two terms fighting against each other. Maybe your neural network says, oh, I want to increase this value. And your loss will always tell you, no, I want to decrease the value. So only if the network is really, like your loss term is really telling, oh, this value is important, you should increase it clearly. Only in this case, you're increasing it. And if the other model is a bit unsure, you have this bias, you prefer to have it not used. And if you have a lot of very small values, it also means that you have, these parameters are not really important and not essentially used. So you somehow, if it's not needed, you're downscaling the number of parameters without like having to try all of them. And how you do it, there's of course different ways. You can do that with the L1 regression, which is just the absolute value, or you can do it with the square of that, which is even stronger than like even preventing it from being more, or you can even what is referred to as elastic net. You can do the same thing with both of them. Any questions to this type of regularization? Yes?
What's the R?
This is our function. So this is what you add here in your loss term. You say lambda times R, and these are possible implementations of R of the regularization term, depending on what you use. If you're using L1 regularization, L2, or the elastic net. I mean, the idea is you have overfitting if you have too many parameters. So the idea is, can we find a network which uses as few parameters as possible? So by doing that, here you prevent a lot of parameters, or you try to make a lot of parameters to be nearly to 0, so mainly not there. So you prefer a solution which uses less parameters, because the general idea is that if you have less parameters, you'll be better in generalization. Okay. Another idea of doing that is to randomly ignore some of your hidden states, or like hidden values. So now if you here have a small example, so you have a feed-forward neural network where you have a hidden size of 4 in the first layer, of 3 in the next layer, and then you have 2 output layers. And the idea is that now during training, you're not training always your whole network, and you're not using your whole network, but you're somehow always removing random parts of the network. And then you try that this sub-network, which is randomly selected, is also performing very well. We are doing that by ignoring values randomly during training, and commonly the value is used as 0.5. So for each of your neural values, you flip a random coin, and if the value is 1, you're using the neuron. And if you don't use it, if the value is 0, you don't use that. So somehow for each like forward pass you're doing, you're using a different type of neural network. So it can be that at one case, these 3 neurons are 0. So you're ignoring that. So in this case, you have the neural network, which starts with our 3 inputs. So you always have the 3 inputs. Then you have 2 hidden values there, K12 and K13. Then you again have 2 neural networks, and then you have the output layer. And then you're trying to optimize this type of neural network. If you do the next training iteration, you might have different neurons active. So in this case, in the middle layer, you do 3 in this one, and 1 in the top, and then on top nothing. So what happens here is that you're mainly always training like a type of different neural network, and you're trying that all of these are somehow giving you a good performance. So what is the motivation behind that? So on the one hand, you're trying to learn redundant features so that important information are not only stored in one neuron, but they are stored in in several neurons. And secondly, you're preventing a bit of co-adaptation. So not that there's a one neuron assumes these information are in the other one, because it can't be sure that this other neuron is there. So it has to be able to do a good prediction in both cases when one other neuron is there and when one other neuron is not there. There's also like a bit of a different view on that. And that is that what you're mainly doing is you train a large ensemble of models. So you're not training one model, but in each iteration, you're training a different model. And just all these models share most of the weights. And in the end, you can use the common model. So if you think about it, this can be viewed as one of the possible subset of models where these three neurons are off. And then in the other case we had before, another one would be off. So you always have a different type of model, and all of these should perform well. And of course, they're sharing the weights of K13 are for all the models the same. That means you really have a huge number of possible models, and you can jointly train all of them together and let them then work together. And again, that is then preventing you in overfitting, because the models, as we said before, they cannot assume so much about the other part of it. So if you think about that, if you have something like 4,000 parameters in there, that means you have, if you randomly drop them or not, in total, you have 2 to the power of 4,000 possible configurations. That is like 10 to the power of 1,233 models. So you have a huge number of possible configurations. You're, of course, not training all of them because you wouldn't have time to go through all of them, but a lot of them are trained, and the model really needs to learn a robust configuration that in all these cases, you get somehow a decent result. Yes, so this is the basic idea. Before we are going into details, any questions about that? Good, then I have a question. If you're now trained there, do you see any problems during inference? Yes?
I mean, it will be acting suboptimal because it doesn't have all the parameters, probably.
Yes, that is, it doesn't have all the, suboptimal is the one part. There's another part which, yeah, I'm not sure if it's worse or better, but the other part is, yes?
The output will be different every time.
Yeah, so there's somehow random output in there. So if you're masking, you get different results on depending on which neurons you're masked. Hopefully, with a good training, it will not be completely different because the model has learned to independently for all the models predict that, but it will not be perfect. So somehow it's, of course, inconvenient if you no longer have a deterministic prediction, but it depends on what type of things you're masking there. And so we have to do it a bit different. And so the idea is, okay, let's try to average this out. So if we then want to now again not have the prediction based on the mask, but we want to really have a prediction based on all parameters, what we have to do is a bit like calculate the expectation value. So what is the expected value that we get depending on the different possible masks? And again, if we would do that just by summing over all, doing the integral, or it's discrete, so we can sum over all possible masks and calculate the output and then take the average from it. We just saw that this might be a bad idea because the number of possible masks, you saw if we have 4,000, it's 2 to the power of 4,000. So this is not really a efficient solution. So we cannot easily just iterate over all possible masks, always calculate the output, and then take the average out of it. So we have to do a bit more better approximation of that. And the nice thing is we even don't have to do an approximation. So let's have a look at the most simple version of that, which is you have two hidden units, two inputs, then you calculate your activation, and then that is your output. You might have later some softmax or something on that, but yeah. So if you think about it, a single neuron looks like we have one weight times our first input plus the other weight times our other input, and that is then the final value. That's like the minimal type of neuron you can have. If you now think about that, there's 4 possible masking strategies. So you can mask this input, you can mask this input, you can mask no input, and you can mask those inputs. These are all the 4 possibilities you have. And the nice thing is, in this case, all probabilities, all of them are equal probabilities. So each of these combinations have like 1/4 of it. If we're doing that now, what we see is here that if we're now really doing like the average of all these 4 examples, with 4 we can do that. So it would be 1/4 times the function we have, if like the mask is both 0, so we take both weights. Then we can mask the second one, so it would be 0 times h2. We can mask the fourth one, which would be 0 times h1, or we can mask both of them, which is 1/4 times just 0. So this is the case. We are masking each neuron with a probability of 0.5. So that means if you now sum this up, what you have is like 1/2 from 0, 1, weight 1 times h1 plus 0, theta 2 times h2. So you have again here your dropout probability. I mean, this is not a mathematical proof. You can do that. It's more like a motivation example, like how to do it. So what we really have to do is, if we're just multiplying all our inputs with the dropout probability, then we're calculating again the correct output and can do that correctly. And it somehow makes sense if you think about this again. If you have these types of inputs, if you do drop out, you're not doing the weighted sum of everything. So K1, 2 goes up, not always, but only in half of the time. So in average, only like 1/2 of these values do. If you would just sum them up, you would have now a lot larger scale in your weighted sum that you normally have. And therefore, the first way of doing it is to multiply a test time everything with your dropout probability. So you can implement that typically in an additional dropout layer in between here. And what you then do is, like at training time, you can drop out by randomly assigning 0 and 1 to this, whether you pass information through it or you don't pass information through it. And at test time, you multiply the values here always with a probability, so with 0.5 in this case. So this is like more a different way of doing that. So it's exactly you're doing this dropout, but like implementation-wise, what you typically have is in between this type of dropout layer, which at training time like drops out randomly then, and at test time, it scales them with P. That's nearly as you implement it. There's one more trick you can do. I mean, normally you're interested in a very fast speed at test time. So it would be nice if you don't even have to multiply them with P at test time. There's one trick of doing that. Anybody aware of that already? The only thing you're doing is you're doing the multiplication at training time with 1 divided by P. So then at test time, you're used to like P times as big ones, and then you have to do nothing at test time. So you're not only dropping them with probability P, but you're also multiplying them, if you haven't dropped them, of course, with 1 divided by P, and then they're like 2 times larger, and then So in test time, you would have now multiply again by p, but 1 divided by p times p is then 1. So you have to do nothing at test time and don't have to do any extra calculation. And then, yeah, what you now basically have is that during training, you're not using all your neurons all the time, but you're only using part of them, therefore learning more like a more robust solution. And then the idea is that during then the test time, you use all the one to have all the power and still have a very good solution. Any more questions to what you then also can do is look at your loss function and at your classification type. And we will look at that as the example of a multi-class classification, which is a very common application scenario for language generation. You often like your classes are also your vocabulary, or for image classification, you have a fixed number of classes. And what you then have to do is like classify all of them, whether they are in or they are not in. And what we see then here is how we're doing it. We said what we're doing is we're applying the softmax function so that we have a probability distribution here in purple maybe, and our loss is this cross entropy loss, which always takes the label value times the logarithm of your probability. So our labels also have the one hot encoding, which is here. So one value is 1, all the others are 0. And this is our output. We're multiplying them. You see that because you're multiplying with this one hot, this sum gets into a single value. It's only like looking at the logarithmic of the output probability of the correct label there. So this is what we are doing by default. If you now compare, this is your output probability and that is your label, and your loss, mainly the idea is that you make these two as similar as possible. And with this type of softmax, there is somehow a challenge that you will never reach the reference distribution. So we are having here a one hot distribution. In order to reach that, you would have to have negative infinity for all the other labels to be really 0. Otherwise, it'll never be 0. So the longer you're training, some of your parameters tend to always get larger and larger, so that these values get very negative and the other get very positive. So yeah, you have a bit of the challenge that you're trying to reach a goal which is unreachable. Because yeah, your label is like discrete, while you always have this type of probability where there's some probability mass always with the others. And therefore, one idea is, okay, we are trying to smooth a bit this reference we want to achieve. We are not saying we have to achieve exactly this, but only like most of the probability mass should be at the correct one, and only like very small fractions should be at all the other classes. How we are achieving them, there's like the general idea of smoothing. So this is our reference distribution, which takes, yeah, most of the probability mass to the correct thing, or like 1 and 0 to all the others. So if we want to do smoothing and we want to keep a probability distribution, the first thing we have to do is like reduce a bit of the probability mass from the correct one. So instead of taking the purple one, we're now taking the blue one, saying that some of the probability mass, although this is the correct solution, is not there. And instead, the probability of the correct label is no longer like 1. The Kronecker symbol here means it's 1 if it's a correct probability and 0 otherwise, but it's like 1 minus epsilon times this one. So it's only like 99% this one or something like that. And then we have a bit of additional probability mass because the sum should still be, of course, 1. And then we can distribute this additional probability mass epsilon, which we're having here, somehow on all the other labels. Since we have no idea at the beginning what other good or bad solutions are, the good guesses are we're just distributing it uniformly to all the others. So in this case, you have now a bit more like a smooth distribution. It's no longer that all probability masses is one class and all the other classes have zero, but only like most of the probability mass is there, and some probability mass is distributed across all the other types of classes you have. Yeah, there's two ways of how you can implement this. The one thing is, or the maybe easy thing is, you can just change your labels. So you don't say the correct solution is our Kronecker distribution, which like 1 and everything else 0, but a smooth direction. Or you can adjust, you can keep the label this way because maybe it's more efficient, because you only have to store one value for everything, and then you adjust your loss function to also include this one into your loss function. Good. So this is somehow first big overview on how to deal with like a bit of overfitting. We looked into regularization, dropout, and label smoothing. And yeah, was a bit our first half. And now in the second half, we want to look more into, yeah, what to do to prevent vanishing and exploding gradients. Before we're doing that, any more questions to the things we covered so far? So the idea in batch norm is that we are somehow trying to keep like the distribution of our hidden values we have. So how this hidden vector looks like, it shouldn't change too much, because if you only have a limited change in that, it means that we'll change less the upper layers. And if we once otherwise do a big change in the lower ones, we'll have a complete different calculation up there. And then all we learned there might no longer be that helpful. So the idea is that we might change it, like how we represent things internally, but the general scale of the model should be, of the hidden states of the difference should be the same. And that is achieved by saying, the hidden state should be like Gaussian distributed. So the idea is shown here. So the idea is that our hidden state x dash, which we're taking, we are taking x, we are subtracting the expectation value from that and dividing it through the variance of x, and so that then for all our hidden states x, which we have, are now like following Gaussian distribution. So I mean, this type of calculation is not really difficult. You could do that just like on top of each hidden state, and then the hidden state no longer like goes very crazy, at least in average, but all are somehow averaged out. Of course, the problem is, how do we now calculate our expectation values of the hidden states and our variance of the hidden states? Any ideas of how to do that? Yes?
We could calculate the statistic moment, like expectation value mean, just sum overall and divide the number, and variance like standard deviation squared.
Yes, exactly. That's how we want to do it. It's a bit more challenging because if we want to really calculate the statistics, we have to go once over all our training data. So this is of course like normalized over all training examples. And of course, it would now be a bit bad if we want to do an update for a mini batch, if we have to iterate over all our training data to calculate the mean and variance. Because again, if you do one update, of course, there's changes and you cannot like say that the same. So we have to do an approximation, but this is somehow quite straightforward. you're not approximating it according to all your data, but you're doing it only based on your current batch. So let's have a bit of look. So this is our input, or we have our X. And on the one hand, each hidden state is like an n-dimensional vector. We always say one hidden state can have like this an n-dimensional vector. And now when we are looking at one mini batch we are calculating, it means we are not only having like one of these hidden vectors, but we have B. So in total, we have this matrix here where like one row is like one hidden state for one example, for one training example, and B is a batch. So these are like all training examples that we look at the current batch. So this could be like for example, the 29th hidden state here is the column here, where you have the value of the 29th hidden state for all your training examples in your current batch. And that means if we now want to estimate the expectation and variance for that, what we are doing is we're summing here over the columns. So we are doing that independently for each dimension. And now we're summing here over all our batches. We're first calculating the expectation values by just doing the sum, and then the variance by taking the difference between the value and the expectation value, and then taking the square out of it. So this we can approximate at least, and then within our batch, these are always normalized, and we are thereby keeping them fixed. So all our hidden states have then somehow a fixed distribution on that. So how you're doing that is typically you do that after your feed-forward layer, and before your activation, you can do the batch norm in here. So what it means is here you have a feed-forward layer. What means is you have here your input, you're multiplying it here with a matrix, and then you're not putting this output directly to your activation function, but you're first doing the batch norm, then you're doing the tangent superbolicus, putting it into your next hidden state, again doing the batch norm, and again doing that. So this is somehow nice because this stays now a bit stable. It's not that your values here, which you input, are like going crazy up and down, but they are always somehow normalized in a way that it's reasonable. So that's a good thing, but of course it comes a bit with a negative point. You're also limiting yourself now. I mean, you're only allowed to have hidden states which have mean of 0. So you cannot have like very large values in there if that's somehow needed. And therefore, there's one additional thing is that, you're no longer allowing to have very big values based on your individual examples, but you're learning a scale and shift so that the values can be learned to be generally in a different scale. So how does it work? We're just learning the mean and variance as additional parameters. So in the step 1, we're doing exactly the same thing as before. We're calculating here the mean and the variance to be then in the next step normalizing our state to be like having mean 0 and variance 1. And then you're doing the shift thing. Now you're saying, but if the model has learned that it's much better that these values are not concentrated around 0, but around something else, it is possible because you have now 2 additional parameters, which is gamma and beta, which allow to shift this one again into some other type of dimension. And you can learn them to be anywhere you want to have them. So what you have then is that you typically have an improved gradient flow, so that the gradient goes faster through that and better. That means you can have also a larger learning rate. It also is less depending on your initialization. and it acts because we are limiting the model to be again having mean 0. It acts also as some type of regularization. In training, that is then somehow most of it, but of course at test time you also have to do that. So you in addition have to also store somehow the mean and variance of your training data to apply the ones from training then also to your test case. Again, it's important then during testing you're not calculating them based on your current batch, because first it might be that you do single example inference, then you cannot do that, and otherwise it would mean that your calculation is depending on the other examples you have, and that of course you don't want to have. Then you would have different outputs depending on if you have different types of other inputs in your data. So there you're storing your mean and variance in there and using them in the calculation. What is happening is a bit shown here. So typically we have the black one is the basic model here. And in the paper they showed, like you see at blue, they have their final performance. The nice thing is if you do different types of batch norm, then you significantly earlier can reach the same performance. So you see, in order to get the same performance, you're here, instead of looking at 30 million examples, you only have to look at maybe 12, and with improved version with less than 5. So you can do a lot more efficient training by not having first to stabilize a bit the scale in the range where the models is, but keeping that in a way fixed. You're getting also a bit better, but this is not really the important thing. It's maybe more important that you are a lot faster and can be faster learn, which of course is very essential in large models, because the larger the model is, the longer the training also takes. So you want to reach your performance as early as possible. Any more questions to this? So the challenge is now that on the one hand, you have a bit of a larger footprint. So since we are normalizing across our batch, so we are calculating the mean and variance, it means you need to have a decent, large enough batch size. Otherwise, your mean and so on will vary too much, and it's not helpful. Furthermore, you can only do that like between each layer, and you now think about an RNN or so where information are transported. You cannot normalize here, and this might then still have a lot of variance. So the hidden state that goes from in the LSTM from left to right, you cannot normalize directly in this way. That's why the other idea which is used is what is referred to as layer norm. And what you do there is that you normalize across layers. So for one hidden state, you say that this hidden state should have a Gaussian distribution, so it should be somehow similar. And that is the only thing you change from the previous one, is that you're not summing here over all your batches, but you're summing over all your features. And then you can again achieve that the value stays more stable, and this is also work. Often batch norm works a bit better, but therefore layer norm can be, for example, applied to also something like recurrent neural networks and things like that. Any more questions to that? Good. Then we have a bit of a recap. We had already this problem of vanishing and exploding gradients. And if you remember, that was when we talked about RNNs. So there we said that if we have a very long signal, what happens, we could calculated our backpropagation and the loss with, sorry. There's the thing. So the loss here with respect to some hidden state is the loss at the last time step times the loss at this time, the derivation at this time step to the next, and so on. And you do that till the step. So if you have to backpropagate very long time, you always like have a lot of more factors in there. You always have, for example, here the factors of WHT we had in there. And we saw that we are multiplying there our derivation a lot of times. That means if we're doing that, either if the value is a bit above 1, we get very large values. And if it's a bit below 1, we get very small values. So this was a bit, a bad thing, because it also meant that, the training wasn't easy. The gradients either went too large or too small, and we can't efficiently learn. And that's when we, for example, talk then about things like the LSTM, where this gradient is a bit controlled. Now, if we think about larger and larger models, you see it here, or hopefully in the picture already, we see the same problem also at another position. So this is now within one row. We backpropagate all the way, we might get very small or very large gradients. Now, if we're talking about deep networks, similar problem can happen. Now, in order to calculate our error here down there, we have to calculate the backpropagation, all the layers from the top to bottom. Although maybe the weight matrices are a bit different because we have different layers, still we get the problem that we always multiply it. We multiply it over all the layers. And then the chance is again that you might lose a very good gradient, and there's no really information coming down there, and it's very hard to train these types of models. So we might need to do a bit. So you see already, especially in this type of deep neural networks, people are often talking about the gradient flow. So in order to train things efficiently, you need to have at all positions like a gradient which can tell you a lot, so how to change. And if the scale goes too small or too big, you can no longer trust it that way, and then it's very getting unstable. So the question is, how can you do this in a way that things are more stable and it's more easy? And the typical approach, which is used in, which you already even have seen, I only shortly mentioned that, and if you remember the transformer architecture, is that you introduce residual connections. So it might first assume or look a bit crazy. Why? I mean, you're now having one layer. F1x can be any type of layer. It can be even one or several layers, can be a CNN layer, a TDNN, self-attention, or anything. And what you're now doing is you're taking your input and you're adding it up on top of that again, which, is not very intuitive in the first way. Why would it make sense to add things up there? But we'll see there's two nice things. On the one hand, we'll see the gradient is better flowing. The other way is also more intuitive. So what you're now need to learn here is no longer, to learn what is a good representation of X in order to do further processing. But what the network only has to learn is what do we need to change in X. And sometimes it's easier to learn that you need to change a bit of things than to learn something completely different. However, there's one additional constraint you're now introducing here about your hidden representations.
Must be the same size.
Yes, exactly. So you have to have, like, if this is like a vector of size 1000 on top, your hidden size is also 1000. However, this is typically not like a big of an issue. So especially if you think about very large networks, what you typically have is not that you're going to small and large sizes all the way, but typically at the beginning, you're once upscaling it to some size, and then you're repeating the same operations over and over again, and then you have the other side. I mean, you might have in between that you go big and small again, but then you can have the residual connection around everything, and then it's still the same. Because you'll have this, if you have a deep network, you don't, I mean, it somehow doesn't make sense that, oh, in this layer we take 79 neurons, and the next layer you take 83, and then 59, and that one, and very different. So you have a general hidden state, and that is all over the same. So that this type of restrictions, that these two neurons need to be the same, is not super important to do that. So why is this helpful in our gradient flow? Again, this is only like a bit of a motivation, but we had our simple feed-forward neural network. If that is just, we calculate f of x. If we then calculate the error to the input to further back propagate that, in order to calculate that, that is the error with respect to the hidden state, and then the derivation of the hidden state with respect to our input. So it's this second time is then the error, because it's just f on x of our function with respect to the input. If we are now looking at our residual one, what we're, and you see if now the partial derivation here is very low, you're getting very low values, and if you do that then several times, you're getting lower and lower and lower values. If you now have residual connections, your hidden state is the output of your layer plus our input, so f on x plus x. If you now calculate the derivation, if you calculate here the derivation, that is f of x derived with respect to xi, and this one is just 1, deriving x with x is 1. So the derivation here always gets multiplied with 1 plus the 1. So you, instead of the derivation itself, you always have 1 plus the derivation. So if these values are very small, they still stay the same. And so you can imagine that then your gradient flows, a lot more straightforward down there than we had before. Another motivation is to doing that is if you take some type of or other network, what sometimes happens is you have here an example of the same task, and once in bluish an 18-layer network and the one in 34. And you see the performance of the 34 is that the 34-layer model is performing worse, which is very, very counterintuitive, because the 34-layer model should be at least as good as the other one, because you can easily produce that by just letting the big model first do the same thing as the smaller one model, and then we just do the nothing for the rest layers. So definitely the 34 layer should be possible to be as good as the other one. But you see it's somehow not learning that in a good way. So it's not able to find an as good solution. If now you think about that as a residual connection, there it's of course a lot easier, because there you can very easily learn to do nothing by just having the function do nothing. That's a lot easier to learn to do nothing than in a basic network like here, where you have to learn to copy the input to the output. So learning to copy the input to the output is significantly more challenging than learning to do nothing. And therefore, especially for deep networks, this type of residual connections are very helpful, and are commonly used in different types of networks. Now you can even combine things. So we now learn that with the residual connection, we are no longer really calculating something new, but what each layer more learns to do is, like, what do I need to change with my inputs to be more helpful or better understandable or anything like that. And that also allows us that we can now combine that with dropout, where we randomly drop out single neurons. But what we can now do is that we're not just drop out single neurons each time, but we can drop out full layers. So this, I mean, before the network doesn't really make sense without a layer, because then, yeah, it might be the model will typically change things, and you cannot input like the third layer into the fifth, although it's used to always getting the fourth. But now you're only doing some changes to it, so you can also have the case that it doesn't do no changes, which means you're mainly dropping out. And that is done in what is called stochastic depth. Stochastic depth, because now your depth of your network, your depth is not always fixed. During training, you sometimes like just throw out some of the networks and just only use the residual connection. Like, for example, here in the third layer, you're not doing really the calculation, but you're just taking the residual connection on, which has then somehow the big advantage. So what you can now do is, if you have a dropout rate of 0.5 for the easiest thing, I mean, typically you don't drop out that much, but if you would have 0.5, it means like in average in training, if you train a 10-layer network, you only have 5 layers. So you only have to, in training, you always have different types of 5-layer networks. You're training only a 5-layer network, but then during inference, you can use your full 10-layer network. So making the training, of course, a lot faster, because at each training run, you don't have to calculate the full layer. That's a bit an advantage compared to the dropout. In dropout, you're not really gaining some training speed, because again, we're doing that as matrix multiplications. So you always have to calculate all values, even though you normally ignore them and like drop out some. It's only for stability. Here, you can like skip a full layer, not calculate that, and therefore have even in addition also like some type of advantage over the calculation. Yeah, finally, two short slides on initialization. So why should we talk about that? So if our problem would be convex, we wouldn't have a problem at all. It would mean anywhere you start, you're always landing in the global minima. And that's a bit like for what original gradient descent was made. The nice thing is, if you have a nice convex problems, if you start anywhere, you're going down and you're ending in your global minima. The problem is neural networks aren't convex, because the error escape is really quite difficult. And so what is typically happening is it's really important to have a decent initialization so that you can end up in a good one. And this means, for example, the scale should be good. You can imagine if you have the wrong scale and your gradients are always around 0, you're not learning anything. So you should learn somehow where the scale is important, where you have good, strong gradients, so that you can learn anything. So if you think about your activation function, if you have sigmoid or any like that, typically for very large input values, they are all around 1. So then your gradient doesn't really change a lot. So you're not learning a lot if you are there. So you have to be somewhere more around the 1 in order to learn something reasonable. So what typically is done, I mean, now at least for the easy case where you just have a feed-forward matrix, where you have maybe m inputs and n outputs, typical things are either to do like a uniform distribution with which is only based on your inputs, so that you have a uniform distribution across values between -1 divided by square root of m and 1 divided by square root of m, or this Scavier distribution where it's based on both your number of inputs and outputs, so -6 divided by square root of m plus it. So then you see, you always try to be a bit like around 0, where typically our gradients are large, so that we can efficiently learn something. If we are doing there like the wrong type of initialization, it might be that all your gradients are nearly 0, and it takes then, I mean, at some point, of course, they are not really 0, they are only like near, so you might learn at some point, but it takes very long. You don't have efficient training, and yeah, can't do that very efficient. Good. So as the last part of today, we want to look at a recent trend to make really large models by what people refer to as mixture of experts. But before we are going there to that, any more questions to what we had before? Good. So the idea here is in general in machine learning, and especially also in deep learning, you are more efficiently if you're not having one model, but you have several models and try to combine them. That is what is referred to as ensembling. We had this term of ensembling already before when we talked about dropout. That's like somehow implicit assembling a lot of models which share a lot of weights. It's also a very successful model if you want to build one very strong model. You just train 5 models, and then you take the average of all the models. So if it gives you an output probability distribution, you average the probability distribution into that. And they can be even like somehow all the same. The nice thing is in neural networks, it's very easy to generate a lot of different types of models. What would be your first way of doing it? If you have one model, how would you generate a second model?
Different in the ways.
Yes, exactly. So it's very easy to get the second, third, or fourth. You just do another random initialization that normally leads to a different model, and then you can combine them. And the nice thing is typically if you combine 2 or 3 models, you have a stronger value. So then, of course, the question is, can we also somehow directly try to train like a combination of models, or like have layers focused on specific inputs so that they're more like used for some? And this is what people refer to as this mixture of experts, which has been there for quite a while, but especially now with large language models. Maybe you've heard about things like Mixtral from the Mistral, where they, like, one of their main contribution is to have a very strong mixture of experts. So yeah, I mean, as I said, so there is a quite long history. At the beginning of the 90s, people looked already into models that, like, the idea is that you're not building one model which can handle all inputs, but based on your inputs, it might be that you're doing different types of models. So if the input is some specific space, you're trying to have an expert which is good at this input space. And if the model is good as another one, then you take a different one. So you have then different like experts as your components, and you have to do some like conditional computation in order to like condition on where to go. And we'll see that is, of course, a bit, again, the challenge in neural networks to be efficient. We said, like, for GPUs, we want to have as few conditional computation as possible. If we are looking at neural networks, there we typically, if we are talking about a mixture of expert layer, we have 2 things. So we have several copies of the same experts. So we have several times the same layer, like always like a feed-forward neural network or a self-attention or anything. Let's assume like more of a feed-forward. Now there's a big difference into what happened before. Before, if we talked about several layers, it means we stack them on top. So the data goes through all of the layers, serial, like first to the first one, then to the second one, and so on. And now in the mixture of experts, it's different. It's in parallel. So the model either goes to several of them, or it only goes, it first selects you have a router which says in which of these n networks that we're having should my input go, and you're only putting it into that. And that also then comes with your second thing, that is like your gating network or router, which decides to which of your n networks you have, you're sending the data. It can be that you send it to all and weight the outputs. It can be that you send it to one, can be send it to two or so. We'll look like what is their different possibilities. So a more simple picture. So the easiest thing, you have two neural networks like expert 1 and expert 2. And these are just your in your layer. And then you have your gating network here that does a routing. And what it does is it takes your input and the output is an n-dimensional vector saying whether it should be in there or with what probability it should be put into the different network. And then you can calculate your final output by, here you see the sum over all your experts, then the gating value, so the probability that it gets into there times the output of that. So the input is once put here, but it's also put into all the others. And now, of course, if your gating function here is not a smooth probability distribution, but it can be also like a discrete function, so that like one value is 1 here and all the others are 0, then you can have the efficiency that you're not sending it to all, but you're sending it only to some of them. So how can you do this type of routing? I mean, the easiest thing, we have to have somehow like a probability distribution over n-dimensional vector. How would you build that? Yes. So we can have just the softmax activation. So what we can do is we can take our input, multiply it with some weight matrix of the gating network, and that is our values gx that we have then there. So this is just telling us, okay, this is the type of probabilities then we have, and then we can send it to all the things. Of course, this has a bit of a disadvantage, and the disadvantage is that all experts need to be calculated. I mean, the idea with the experts is a bit you distribute your work and you have a lot of parameters, but you're always only using some part, and the parameters can somehow focus on things which are difficult. So in this case, of course, you're putting weight on the different ones. So some are more important than others, but it's not that, yeah, you still need to calculate all of your experts, which, yeah, might not be somehow super convincing, because then you haven't saved them. And yeah, therefore there is also other types of ideas. The one thing is what is referred to as a noisy top K gating. So the idea is that we're not sending it to all, but only to the top K values. And you'll see this can be quite dramatically reduced by K of 2 or even 1. So what it means is you're taking, again, your hidden state is just multiplied, and then we are putting here some additional noise in there. Maybe you're not always I mean, the problem a bit with training with fixed top K gating is that if you don't add noise, it might very fast go into that it's always using heads 3 and 5. In all the examples, use 3 and 5, and then you don't have the power. So you want that, of course, all your space gets a bit like evaluated, and then one technique is to add this additional noise. What you now do is that you're not taking all your K elements, but you're only taking the top K. So you set all the top K you take as value, all the others you set to minus infinity, which means that then after the softmax, all except the K has 0 probabilities and you're only using them. So yeah, with this, you can then be more efficient, because you might not need to calculate all of them, but only some part. Of course, things will get a bit more complicated, because if you now think about one batch, it means that within a batch, it's not that all are sent to the same experts. It can be that some are sent to one expert and some are sent to the others. If you think about sequences and you're doing that at each position, things get even more complicated because it means that even for one sequence, some tokens get sent to the one and some tokens get sent to another one. And this, of course, gets more challenging if this is a very uneven distribution. And that even often happens that not really all experts are used very, I mean, you want to have a uniform distribution over there so that all experts are somehow used. The problem is, by default, often it happens that maybe by chance, some of them are occurring more often at the beginning. Then there are some more reasonable results and some which have been not really well initialized yet. And then mainly some small subset of experts are used. And therefore, there are several ways of trying to address that. One is, again, we had this idea already before. If we want to achieve something specific, what we can do is we can add additional losses. And again, you can here do that. So you can add an additional loss that you have similar number of examples per expert. So you calculate how many examples are going to each expert, and then you again try to prevent that, and you want to have that all your experts are used similarly often. For example, by looking at your softmax, you should have a distribution which is uniform so that each of them are often is used quite often. And then before we are looking at two concrete examples, if we again, I mean, this is done typically for large scale models. So the nice thing what is typically done then is that, I mean, I said this type of branch calculation is difficult. So what is often done is expert parallelism. The idea is that if you have now 5 GPUs where you run your model, you distribute the experts to the different GPUs, and then on GPU 1 there's one expert, and GPU 2 there's is the other experts, and you see then typically you have here, this is from a transformer, you have experts for maybe a feed-forward layer, and in between you have other types of layers like multi-head attention. So you have here on device 1 to E, you have exactly for the shared one, the same networks. But if you have here the experts, they are distributed. So on GPU 1, there's expert 1. On GPU 2, there's expert 2, and so on. And on GPU 3, there's expert 3. Now if you're processing your examples in parallel, you process them in parallel, then here you have to do the dispatcher that examples go to the right example, to the right GPU. So if it was distributed to GPU 1, it should go to GPU 1 and so on. Then you calculate here your forward path, and then you can continue. Thereby, the expert parameters have only to be in one example. So that means you can now increase your number of parameters, but since it's distributed over 5, you don't have to really it's still, if one expert fits into the GPU, all your experts will fit into the GPUs because they are distributed and always only one is done. Good. Any questions before we are looking at two examples? So two, often used examples are, the one is the G-share transformer architecture, which does, as here you've seen before, there's a top 2 gating. So mainly means you're always sending each example to 2 experts. And the routing is a bit different. So the first one is selected based on the highest probability one. So you always set it to the expert with the highest probability. But then the top 2 is sampled according to the probability distribution. So what is the difference? So if the highest one is probability 0.5, it directly goes there. If now the second highest probability is expert 3 with probability 0.3, it doesn't definitely go there. It only goes there with not 0.3, but then 0.6 probability, and with some other probability to the other ones. So that is samples. And again, it's like making sure that you're not too fast, like converging to a fixed type of expert. Since they are doing this sharing of experts, you now have, of course, this load balancing gets even more important, because this, of course, only works if somehow they are well distributed. If now everything needs to go to GPU 1, because GPU expert 1 is doing all the doing all the calculation, then GPU 1 has to do a lot of calculation, the other do nothing, so that doesn't really work. So how this is handled is that you have like an expert capacity, so that the maximum number of examples that you can put into this expert. And if there is too much, we can again make use of our intuition we had before. We have residual connections around here. So that means, yeah, if we can't calculate it, we can also still do nothing. It's not a perfect solution, but it should somehow work. And so they have the capacity, and if there's too many tokens for one expert, we just skip this calculation and go to the next one. Another example is what was published as a switch transformer, which is again a transformer where you do this experts, and there they even could run it with like a single expert, so it's always sent on to one expert, which means that you can now calculate the expert capacity. So yeah, how much needs to go to each expert. And the nice thing is, of course, you need a bit of overhead. So because it will not always be perfectly distributed. But if you set this capacity to 1.1 or 1.25, only a bit higher than 1, which is like if it would be perfectly, then you get typically very good results. So you only need a bit more memory, and it's really well distributed so that it's using all the experts and well performing. Good. So to summarize, what you hopefully remember from today is we had different types of strategies to prevent overfitting. We talked about normalization. We talked about dropout. We talked about residual connections. And also at the end, to build really large models, we talked about this idea of mixture of experts. Any more questions? Good. Then thanks again, and see you again on Thursday.